everybody. Today we're going to look at section 5.5, which is titled Net Change as the Integral of a Rate. So if you're going to compare this section to something in the past, think about when we talked about deriving the position, which resulted in our velocity equation. And if we then derived the velocity, that got us to our acceleration. So here we're going to say, well, what is the integral of velocity then? So if we integrate velocity, that will bring us back to our position. Okay. And in the beginning of this chapter, I did use a velocity curve. For example, if we had a velocity curve that was linear, right? And we wanted to know total distance traveled, if we found the area under this curve, that ends up giving us exactly what we would be looking for. Okay, so this section investigates a little bit more the difference between displacement and distance traveled. And another important note before I keep going is some of you might have already discovered this, but your calculators allow you to evaluate definite integral. So on your calculator, you may use this for this whole section. And moving forward, I'll let you know when you can use calculator, when you can't use calculator. But this section is really assessing your ability to set up an integral rather than evaluating an integral. So here, absolutely use it, calculator, and then the keystroke is Math 9 for the TI 83s, 84s. So theorem number 2 here, the integral of velocity. For an object that is in linear motion with velocity v of t, then the displacement during time t1 to t2, that interval, that closed interval, would be equal to the integral of the velocity. Okay. Versus the distance traveled. So there's a very subtle difference, but it makes a major change in the answer, right? Displacement takes into account that sometimes it's positive, sometimes it's negative, and it would actually do the subtraction. It would allow the positive and negative to cancel out. Whereas distance traveled, for example, if I travel north and then I return home and travel south, if I treated that as a displacement, it would say that I traveled 0 miles, and we all know that that wouldn't be accurate for some kind of a road trip, for example. So we would always want to use distance traveled there, and we would use absolute value symbol. That way it takes all of that negative area and flips it positive. So it'll be really subtle in a word problem. You'll be looking for the words displacement versus distance, and when you see distance, you apply your absolute value symbols. So the first example, a particle has a velocity of v of t equals t cubed minus 10t squared plus 24t dt meters per second. The dt is just put in there again because this is an equation that was previously derived with respect to time. Compute the displacement over 0 to 6. So we are just setting up our integral. Oops. Minus 0 to 6. We put our equation in there. Now it's specifically saying displacement, so we can do number 1. So t cubed minus 10t squared plus 24t dt. And you can do this one by hand. It's not too difficult. It would be 1/4 t to the 4th minus 10/3 t cubed plus 12t squared, evaluating it from 0 to 6, right? So the 0 would be nothing, and the 6 you plug in and calculate, or you may Math 9 this. Either way, you'll get an answer of 36. And the unit would be meters. Next one. Find the displacement over the time interval from 1 to 6 of a helicopter whose vertical velocity at time t is v of t equals 0.02t squared plus t in meters per second. So we set up our integral from 1 until 6. We put in the velocity equation. dt, when we're entering this in the calculator, all those parentheses would be relevant. Math 9, or by hand still at this point, that's your preference, but again, you don't need to. I'll show you the work. For part of it, but ultimately your answer is 18.93 repeated meters. That's how far this helicopter has ascended in the time period from 1 to 6 seconds. Now this next one, just this little word of total distance traveled versus displacement over the time interval 0 to 3 pi of cosine t. Well, we set it up the same way, and yes, you can math 9 this, unless it was a question that was non-calculator, which in this case we would want to practice. You saw this in previous examples. Right? If this was something that we would need to do without a calculator, you have to figure out, well, when is cosine positive, when is cosine negative, and split this up into adjacent integrals. And this is a pretty big interval, 0 to 3 pi. Right? If I were to graph this as a normal cosine, we would go here, we would cross over, and we would end here at 3 pi. Sorry, it's not perfect, but here's 5 pi over 2. Here's 2 pi. Right, so here's 3 pi over 2. Here's pi. Here's pi over 2. And of course, 0. Right? So we can see where these negative regions are. Let me change colors real quickly. Right, all of this and that, those are negative, so we need to subtract them or negate them to flip them and turn them positive. So this is equivalent to 0 to pi over 2 is already positive, so we keep the cosine t dt as is. The second region is negative, so I need to negate it to flip it from pi over 2 until 3 pi over 2. I've already put the subtraction, so I don't put another negative. Then from 3 pi over 2 until 5 pi over 2, it's already positive. And finally, from 5 pi over 2 until 3 pi, I've subtracted, so I've negated, and I've gotten what I need, right? So then from here, let me just show you how you can enter this even on Desmos and get the correct answer as long as you do input the absolute value symbols. Okay. So I realize now that I came back to the screen, I don't think when I switched screens that the recording continued. In class, I'd be happy to show you on Desmos or on the graphing calculator. But what I just did is I went to Desmos and I used absolute value symbols correctly, inputted it, remembered the dt or dx at the end, and evaluated to get 6. Theorem 1, we reversed it here, but net change as the integral of a rate says that the net change in position, s of t, over an interval t1, t2 is given by the integral. Integrate t1 to t2 of s prime, which s prime, of course, is v of t, and that's equal to st2 minus st1. So same idea, but what this allows us to do is rather than thinking of it as a distance, which is the most obvious application, we can now think of any kind of change, right? We can think of revenue, or in this case, water leaking from a tank. And the next problem, the amount of bicycles manufactured, any kind of change over a time period, okay? As long as we're given a rate. So this example, water leaks from a tank at a rate of 2 plus 5t liters per hour, where t is the number of hours after 7 a.m. That's the part that's subtle but important in these problems. They define t, and you don't want to just take 7 as your limits of integration, right? The question here is how much water is lost between 9 and 11, and we wouldn't want to use 9 to 11. Hours since 7 a.m., we would then use 2, because 9 is 2 hours after 7, and 4, because 11 is 4 hours after 7. So we integrate from those limits of integration. We integrate the rate, the velocity, essentially. Again, you can do it by hand, or you can put it in calculator and do math 9. So 2t plus 5 halves t squared from 2 to 4, evaluated will come out as 34 liters over a 2-hour time period. Okay, a couple more examples here in this lesson. So a factory produces bicycles at a rate of 95 plus 3t squared minus t bicycles per week. How many bicycles were produced from the beginning of week 2 to the end of week 3. Usually our limits of integration are always the challenge. The rate is given clearly, and we have to think about, well, beginning of week 2, well, that means we want to start at 1 because that will then include all of 2. End of week 3, so we need to end at 3. That will also include all of week 3. So calculator or by hand, 95t plus t cubed minus 1/2 t squared, and that will end up with 212 bicycles. This is the type of problem that you're going to see quite a bit with the AP. Taking a look at a table of values and using this same concept to still come up with a total displacement or a net change for something. And essentially we're using a combination of what we're going through here, some notation, with rectangle approximation. Okay. So a number of cars per hour passing an observation point along a highway is called the traffic flow rate, Q of T, in cars per hour. So here's an example where we're not given a function, we're given some information, some real-life data. So think about the formula for net change. What quantity is represented by T1 to T2 integral of Q of T dt? So that's the traffic flow rate. So this integral is representing how many cars are going to pass from T1 to T2. So the flow rate is recorded at 15-minute intervals between 7 a.m. and 9 a.m. Estimate the number of cars using the highway during this 2-hour period. So remembering that if we're looking for total number of cars and we're looking at an integral, then we're also looking at the area under the curve. Right? And the first way we learned how to do the area under the curve was through rectangle approximation. So if we want to truly get a good approximation of this integral of Q of T, specifically from 7 to 9 a.m., then we're going to use left and right Riemann sums in order to come up with an approximation. So we'll start with our left hand Riemann sum. And I'm just going to put n for now because the table of values kind of dictates the number of rectangles that we truly have. And remember that the formula for this is your delta x, or the change in x's, multiplied by the heights, or the y values. So we have 15-minute intervals, but really the unit that we're talking about is an hour. So our delta x, which does equal 15 minutes, is also equivalent to a quarter of an hour. Okay, so right here I'm going to put 1/4. And if I'm doing left approximation, I would begin with the first y value, and I would work across, and I would stop at the second to last y value. Right? If that they would be the left-hand corners of my rectangles if I were to sketch this out. So 1044 plus 1297 plus 1478, 1844, 1451, 1378, 1155, and 802. So add them up, multiply by 1/4, and you get 2,612 cars. So that's our left approximation. We want to do the same thing doing the right-hand approximation. Delta x is still the same, and this time I'm going to start with 1297, and I'm going to go all the way to 542. And this comes out to be 2,487 cars. So a true approximation from 7 to 9 of Q of T dt would be the average of ln and rn together, right? Essentially m. But when you have a table of values, you can't really find m without doing an average. So approximately 2,550 cars pass at this traffic location between the hours of 7 and 9 a.m. So I'm going to leave this other example, which is a table of values problem, for us to do in class. It's an important one, again, because this is the type of question that you may see both on a regular assessment and on the AP exam. Okay. And then the final one that's on this page, really just in closing, suppose the downward velocity of a skydiver is given by v of t equals 30 times 1 minus e to the negative t feet per second for the first 5 seconds of the jump. Compute the displacement over the first 5 seconds. So because he or she, they are traveling down, in order for this to show the downward, I can change my limits of integration, and that will automatically give the negative result. Okay. So the skydiver descends 120.2 feet in the first 5 seconds. Okay. In terms of your problem set, double check what the Canvas website says. It may or may not be the same as that. So check in there for your work.